Hello everyone, thanks for attending our demo about HAR-GCNN, which is a deep graph CNN for human activity recognition from highly unlabeled mobile sensor data. This is Abdullah Muhammad, I am your presenter today. The motivation for our data ground truth annotation for HR is a difficult task. For example, sometimes you might ask user to annotate what he done as an activity. He might be doing some couple of activities in parallel. He might not have enough time to do this kind of labeling task. He might do this labeling later on the day. So it's very difficult to get an accurate activities labels, and it full of errors, and was our main motivation for developing our method. We hypothesized that humans follow a chronological order of activities. For example, on a daily basis, you might be waking up in the morning, then you take a shower, then you eat a breakfast. And you might be doing this on a daily basis actually. And for example, as a habit, you might be eating your lunch while watching a TV or typing on your phone. And this kind of activities you do on a daily basis. And it's kind of embedded into your routine and into your nature as a behavior. So we hypothesize that we can use this kind of correlation between activities to identify all the activities. And our main focus is if we have at least one known activity in your day, can we know all the earlier activities and the next activity that you might do by knowing this one thing? So in our paper, we hypothesized this hypothesis and we show that actually it is true and it exists and we can use it to identify your activities. Why graph representation exactly? Graph CNN has two features when compared to prior deep models. In RNN, there is an accumulation between errors between the prediction steps in which CNN-based methods that deals with temporal data doesn't have. Also, the CNN doesn't have this issue in RNNs, but doesn't have this relationship between activities or between nodes in which graph CNNs have this thing. So basically, graph CNN has two advantages over prior methods. The contribution of our work is first a formulation of HAR problem that explore the chronological context of activities. We also propose a novel training mechanism that generate the models. Also, we actually show extensive experiments and comparison with baselines. We use two datasets to analyze our method. The first one is the extrasensorial dataset, which is collected in the wild. The second one, the PubMap dataset, with a scripted dataset. The thing is, the extrasensorial dataset doesn't have a scripted thing, so basically the chronological order can be discovered. On the other hand, the PubMap dataset had the script, so basically we show in the results that the models learn the script and ignore the features recorded by the PubMap dataset. The training and testing is 2 to 1 split. The input to our model is a graph. So we construct the graph by first defining the vertices, and the vertices contains two things. The first one is the features or the measurements, and second one is the corresponding class label. We also use edges to represent the relationship between things. We set the edges to be 1, so the same value goes for the adjacency matrix that just corresponds with these edges. We represent missing activities as zeros. After formulating our input graph, as we described before, we use a graph CNN to process this graph. So the graph CNN receives actually two inputs. The first one is the vertices, which contains the measurement of the sensors and the corresponding label, which is either is known or unknown. And also to receive the adjacency matrix, which is a representation of the edges of the graph. And we use a normalized version of the adjacency matrix. This normalized version actually is a Laplacian equivalent of the adjacency matrix, and we can see that there is an etc term here. We use an identity matrix, and this identity matrix here, it emphasizes on the values of the node itself to be considered within the kernel function of the graph CNN, and the Laplacian formulation of the adjacency matrix gives a weight for the all values of the edges or all values of the nodes that sums to a unity. So basically we don't have an explosion in our gradients. So the graph CNN acts exactly as a CNN, but the main thing or the main difference that it weights the value or the contribution between the edges by using the adjacency matrix. And this is the main difference between the GraphCNN and CNN, and this is basically why our method is much better than the prior ones. Afterwards, we use a sequence of CNNs to process the embedding coming from the GraphCNN. So one reason for not using GraphCNN all the way long, that actually what we care about eventually is the label of the classes. We don't care about the edges anymore. The second thing, that there is a known issue in GraphCNNs, that when you go deeper with it, they're kind of performance degrading. So basically we use CNNs here as a replacement for the GraphCNN to construct our whole model. We use two baselines. The first one is CNN baseline, and the second one is an LSTM baseline. Both baselines share the same depth, the same number of parameters, and trained with the same settings as our model. They also, we see that in the CNN baseline, we have all the activities in a format like a picture. On the other hand, in the LSTM baseline, we have each activity inputted into the network, and then the next one to predict the label of this activity. Our training mechanism helps our model to generalize and mimic the behavior of unknown activities. So we either randomly hide a class, or we add a noise to one of the measurements to generalize the model. And then we use either our model or the baseline with a corresponding loss function that differs between the extrasensory dataset and the bump-up dataset. Coming to the results, we have this table here that first we have the number of activities. Second is the percentage of the missing labels. All the results here are reported on the test dataset. And the results are the F1 score over the accuracy. And actually we use accuracy to see exactly how accurate we are, but it's not really representative. This is why we relied on the F1 score. And then we have the extrasensory dataset and the PAMAP dataset. So as a general notice, the performance of HAR-GCNN is actually much better than the baselines of the CNN and the LSTM corresponding ones. The second note is that we know that the CNN actually performs better than LSTM, and this is basically our assumption at the first of the paper, or our observation that RNN-based models tend to diverge over time when we have this number of activities, or actually like what we said before, that they accumulate errors through predictions. And we can see that the CNN has a better performance, but still not as good as the GCN, because it's missing this correlation between the nodes itself. It misses this adjacency matrix that represents the relationship between the nodes. So we can see that the performance on under 33% or 66%, it's much better, still the same thing. And there is a general notice here that the extrasensory dataset have this normal behavior of accuracy, like the F1 score, you see it. But on the other hand, when we go to the PAMAP dataset, we notice that we almost have a perfect F1 score, and we also have a perfect accuracy. And this happens everywhere in the PAMAP dataset. And if we thought about this, there is a main difference between the extrasensory dataset and the PAMAP dataset. The extrasensory dataset was actually collected in the wild. There was no script for the users to follow in doing their activities or executing the activities. But on the other hand, the PAMAP dataset, users were asked to do a script of activities. And what happens here, that this high accuracy, we rely to that the models actually discovered this script. So basically, the features or the measurements did not matter in this context, because the script was there. So basically, the model still needs the systematic bias that exists in the dataset. And this is really important because it shows that the chronological activities can be used. And once we have this bias or this static chronological thing, we have this improved result, we have this huge result, almost perfect. But on the other hand, in the extrasensory, because it was collected in the wild, we don't have such a performance. We still have some room for improvements. Thank you for attending our presentation. We are open for any questions.